Last time, we talked about sampling distributions. Today, we will extend on that idea to talk about how we can use those sampling distributions to begin to help us make inferences about a population. Let's start by talking about one of the most important people in statistics, William Gossett. William Gossett was the chief experimental brewer for Guinness Brewery in Dublin, Ireland in the early 1900s. As part of his job, Gossett had to assess the quality of the batches of beer that they brewed there. To do this, he would take samples of the beer and test it to make an inference about the quality of the overall batch. Because he didn't want to literally drink their profits away, the samples were always small. At the time, the common way to do the test to make an inference about the quality was to take the sample and use the mean, standard deviation, and sample size to complete calculations and determine the quality. However, he found more often than he expected, his inferences about the quality of the full batch were wrong. When he couldn't figure out why this was happening, he decided to take time off and earn a graduate degree in statistics. Here is what he learned while he was in school. This is the data from one of the data sets he worked with. It measures the heights of 3,000 people incarcerated in the area. This was his population data set. He then created a sampling distribution from the population data using a fairly small sample size of 4. Recreating his work with technology, it would look something like this. Remember that we have learned that this sampling distribution should have the same mean as the population, and you can see it does, and a related standard deviation by the original standard deviation divided by the square root of n, here the square root of 4. And it should look more normal and narrow than the population. Now, just like when we worked with z-scores previously, you know that we like to standardize our data so that we can use standard tables and charts to calculate areas for any set value. To standardize, remember, we take our observation, subtract the mean, and divide by the standard deviation. For a sampling distribution, that looks like taking a sample mean from a single sample, subtracting the mean of the population, and dividing by the standard error, or the standard deviation of the population over the square root of the sample size. When we do this, we have what we call a z-test. Just like we did before, when we plot all of the z-scores, we now have a distribution of standard scores, or a standard normal distribution. But here's where Gossett started to realize the problem. To calculate those z-scores, he had to know the standard deviation of the population. But in reality, when he was testing his batches of beer back at Guinness, he had no idea what the standard deviation of the population was. Instead, he would just use the standard deviation for the sample he had. But remember, each time we take a sample, we get a slightly different result. Because of this, the distribution we create by using S, the standard deviation of the sample in our calculation, instead of sigma, the standard deviation of the population, actually looks a little different. On the left, we have the Z distribution, or standard normal distribution. On the right, we have a distribution called the T distribution. It's created by almost the identical formula for standard deviation, but instead we divided each time by the standard deviation of the sample taken rather than dividing by the same standard deviation of the population every time. As you can see, the distributions aren't identical. Overlaying them, you can see that the T distribution in red is both flatter and wider than our Z, or normal distribution. Here is an exaggerated image of what Gossett found. Our Z, or standard normal distribution, is in blue. But when we create a T distribution, because we don't know the standard deviation of the population, we see that the shape of the distribution actually will change based on our sample size. For a larger sample size, we will have a fairly normal sampling distribution. But when we have a small sample size, like what he was working with, we have a flatter distribution. Here is a less exaggerated and more accurate image. You can see here that by the time we get to a large sample size of around 20 or 25, we do have a fairly normal distribution. But these small sample sizes make a flatter shape distribution and were responsible for the errors he was getting in his results. While the t-distribution is similar to the standard normal in that it will have a bell shape, be unimodal and symmetrical, and the mean will still be 0, the height of the distribution changing will cause some differences. So how did he realize that this shape change was affecting the results of his analysis? Well, since t doesn't follow the standard normal distribution exactly, the cutoffs we learned for the empirical rule, or that 68, 95, 99% rule, will not be the same in a t distribution. While in a standard normal model, exactly 95% of scores fall within 1.96 standard deviations of the mean always, the markers that mark off the center 95% of scores in a t distribution vary by sample size. Specifically, we say that the t-distribution shape depends on something called the degrees of freedom. The degrees of freedom is a parameter that is calculated typically by taking the sample size minus 1. So, if we know the size of our sample and subtract 1, we can look up the probabilities for corresponding t-statistics for any sample mean, just like we could with our z-scores. We will use this t-distribution to help us run several statistical tests. Gossett's work, published under the pseudonym Student, allows us now to make more accurate conclusions from even small samples of data.